Hello everyone and welcome to the video for Chapter 4 Section 1 on angle measures. This is where we're going to be starting with trig, so that'll be a lot of new stuff and interesting stuff, so let's get going. To start out with, our skill objectives for this video are 1. To convert angle measures between degrees and radians. Number 2, find the complement or supplement of an angle. We'll probably talk a little bit more about that in class. Identify coterminal angles. Calculate the length of an arc or area of a sector. Our conceptual objectives for this video are 1. Understand that degrees and radians are angle measures. Number 2, realize radians are a unitless or dimensionless measure. And the third thing is understand that relationships between linear speed and angular speed. So we want to find that relationship. When we start out with angle measures, there's a couple things you need to keep in mind. Angles are measured in either degrees or radians. And the other thing is angle measures can be any real number. We can have a positive angle measure, we can have a negative angle measure. Now, to really get an understanding in terms of and identifying what the angle measure is, we do have to look at what is called standard position. When I talk about standard position of an angle, it means that the vertex is going to be at the origin and the initial side is going to be on the positive x-axis. So what we have up here in these two examples, here and here, these two examples, the angles are in standard position. In other words, there's our vertex and it's at the origin. Now, when an angle is in standard position, I can determine if it has a positive or negative angle measure by the direction of rotation. If I rotate the angle, do the rotation in a counterclockwise direction, like in this case here, when I'm going counterclockwise, it will be a positive angle measure. When I have a clockwise rotation, I will have a negative angle measure. It is also important to remember that when we talk about an angle measure, it is the amount of rotation that the terminal side has from where it started. So it's always going to start on what's called the initial side, and then the terminal side will have the rotation and it will end up somewhere. And the amount of rotation is what's called the angle measure. Now, we do have two different measuring systems for angles. One is the degree. That's the one you're most familiar with. An angle formed by one counterclockwise rotation has a measure of 360 degrees, and it's denoted with the 360 and then this little degree symbol that's right above it. Okay, that is what a degree. That's how we go through and came up with the degrees. It is a fairly arbitrary, and that's one of the issues we have with degrees. Is it's not it's not related in any way to the circle. It doesn't tie parts of the circle together, and it causes an issue in terms of calculations. Radians, on the other hand, when we look at angles in radian measure and working with those, our lives, a lot of times the calculations are a lot easier, but you are less familiar with radians, and so generally people are not as comfortable with it. So the definition we have for a radian, we have a central angle. What that means that the vertex of the angle is in the center of the circle. If a central angle intercepts an arc of length equal to the radius, then the angle has a measure of 1 radian. So when I look at this angle, my sides come off like in that direction here and here. And what happens, it will cut a piece of the circle. And if the length of that arc is the same length as the radius, then I would say theta has a measure of 1 radian. So how do we go about finding the radian measure? Well, really what we're looking at is we have a central angle, theta, in a circle of radius r, intercepts an arc of length s. Then the measure of theta in radians is given by theta equals s over r. Now, the other thing what you have to recognize from this is that both s and r have the same units. So if we are looking at inches, when I look at r, my radius is in inches, and the length of that arc is in inches. So therefore, when I take s inches over r inches, when you reduce that, you actually get rid of the units. So the radian is a unitless measure, which actually also helps us out in some of our calculations. The other thing you have to realize on this, we know 1 time around the circle is 360 degrees. 1 full revolution, the arc length, if you will, is just going to be the circumference. So S would be 2 pi r over r. When you reduce that, you find that 1 full revolution is equal to 2 pi radians. One of the things that we're going to ask you to do is also to convert between degrees and radians to degrees. So we have 2 conversion factors. The first one, to convert degrees to radians, what I'm going to do is I'm going to multiply the degree measure by pi over 180 degrees. To convert from radians to degrees, I'm going to multiply the radian measure by 180 degrees over pi. Let's take a look at a couple examples of this. Here's ones where we're going to convert from degrees to radians. So I want to convert 30 degrees to radians. Sorry about the pen, it's been causing me a little trouble lately. But 30 degrees times the pi over 180 degrees. When I bring that together, I have 30 degrees times pi over 180 degrees. You'll notice the degree symbols cancel out, the units cancel out, and 30 does go into 180 6 times, so the result is pi over 6. Or if I put that in my calculator, it comes out to be about 0.524 when I round it off. Let's look at 125 degrees to radians. Same thing, 125 degrees times pi over 180 degrees. Well, when I put that all together and I reduce it, I end up with 25 pi over 36. That would be the exact answer. And if I put that into the calculator, I get 2.182 as in terms of about 2.182 in terms of radians. Now let's look at a conversion to go from radians to degrees. In this case, I'm going to go through and take 2 pi over 3, and I want to convert it to degrees. And so when I put that together, I have the 2 pi over 3 times the 180 degrees over pi. And the first thing I'll notice, that when I multiply this out, I notice that the pi's will drop off. And the other thing I know is that 3 does go into 180 60 times. So it'd be 60 degrees. And so the result would be 2 times 60 degrees. It comes out to be 120 degrees. One common misconception about radians that a lot of students have is because a lot of the angles we work with when we're dealing with radians have pi in it, that they automatically assume that if they see a pi, that's radians. If they don't see a pi, it's not radians. Well, in this case, what we have here, I have a problem where I want to convert -14 because there's no degree symbol. I know that is radians. So it doesn't have a pi, but we're still dealing with radians here. And I want to convert it to degrees. Well, in this case, when I go through and do that, I'm going to take the -14 times the 180 degrees over pi, and I have to multiply that. Well, you notice on that, that's not going to simplify any. And so what I do is I just put in a problem like this, we're going to approximate it. And I put that into my calculator, and that comes out to be about equal to -802.141 degrees. And I'll just get that by just plugging it into the calculator. Another thing we're going to be working with is coterminal angles. And what that means is that we have 2 angles that are in, when we place them in standard position, they have the same terminal side. Because they are in standard position, they both are going to have the initial side on the positive x-axis, and their terminal sides are going to be in the same location. They'll just have a different amount of rotation. So what we have to do is identify, how do I go through and find coterminal angles? Well, what I have to do is I just add or subtract 1 revolution, which can be, if I'm working in degrees, 360 degrees, or if I'm working in radians, 2 pi. So let's look at an example here. In the first example I have, a theta is 45 degrees. I want to find coterminal angles. Well, one of the things I can do is just add 360 degrees. So that gets me, when I take 360 plus 45, I get 405 degrees. Because I can always add another revolution, I can add another 360 to that, and when I add that, I get 765. So I know 765 degrees, 405, and 45 degrees are coterminal. If I go and add another 360 degrees to that, I will get the angle 1,125 degrees. And because, again, we found that by just adding one full revolution, which is 360 degrees, all of these up here are going to be coterminal to 45 degrees. The other thing is, because angle measures can be negative, I can also subtract 360 degrees and still get a coterminal angle. So when I take 45 minus 360, I'm going to get negative 315 degrees. If I subtract another 360, I get negative 675 degrees. If I do it again, I get negative 1,035 degrees. And I can keep doing that as well. Every one of these angles here would be considered coterminal to 45 degrees. Now when we're working in radians, the idea is it's the same idea. We can keep adding or subtracting a revolution, but the issue that we have is that we're adding or subtracting 2 pi. So, for example, I took pi over 3. I'm going to let theta equal pi over 3, and I want to find coterminal angles to that. Well, to get one coterminal angle, I'm going to add 2 pi, which I think of as 2 pi over 1. I get the common denominator, so I'm going to multiply top and bottom here by 3. So I get pi over 3 plus 6 pi over 3. And so I get 7 pi over 3. So I notice every time I add 6 pi over 3, which equals 2 pi, I'm going to get another coterminal angle. So I have 7 pi over 3. If I add another 2 pi to that, it's going to come out to be 13 pi over 3. If I do it again, I'd get 19 pi over 3. The other thing I can do is I can always subtract 2 pi, or subtract that 6 pi over 3. So if I took pi over 3 minus 6 pi over 3, I get negative 5 pi over 3. And again, I can do it again. I can get a negative 11 pi over 3, then negative 17 pi over 3, and so forth. Each time, just adding or subtracting one full revolution. And you have to be aware of which unit you're working with. If you're working with degrees, one revolution is 360 degrees. If you're working in radians, one revolution is 2 pi. Now let's take a look at the 2 types of speed that you're going to have to worry about, you're going to have to work with. The first one is what's called linear speed. So if you have a point P that's moving along the circumference of a circle at a constant speed, then the linear speed, which we use as v also sometimes people will think of it as velocity, but we're going to use it as linear speed right now, is given by v equals s arc length over t. If a point, so what's happening here on this one is, on this particular one, is that the arc length is going to be how the particle has moved, how that point has moved along that circle. And every time it goes around, it's covering the circumference. And so that's how we're going to calculate that. S is going to be the distance it's traveled over the amount of time. Now, if a point P moves along the circumference of a circle at a constant speed, then that central angle is also changing, and it's going to be the central angle theta that is formed by the terminal side passing through P also is going to change with time t at a constant speed, and that is called the angular speed. We use this weird looking W thing, which is called omega, and it's given by omega equals theta, that measure of the central angle, divided by time, where theta is in radians. Let's take a look at an example involving linear speed. What I know on this one is I need to determine to find my linear speed, I need to know the arc length, and I'm going to divide it by the time. Well, in this case, we have a car that's traveling at a constant speed around a circular track, and the circumference of that track is equal to 3 miles. If the car records a time of 12 minutes for 7 laps, what is the linear speed of that car? And we're going to do it in miles per minute. Well, in this case, because the circumference is 3 miles and I'm doing 7 laps, I know, in this case, that my arc length, if you will, S, is going to equal 3 times 7. 3 miles times 7 laps, which is going to be 21 miles. And now, since the car was going for 12 minutes, I know that its V is equal to S over T, which in this case is going to be 21 miles over 12 minutes. And when you reduce that, that is going to come out to be 7 miles over 4 minutes. Or that's going to be equal to 1.75 miles per minute. In this next example, we're going to look at an angular speed problem. A lighthouse in the middle of a channel rotates at a constant rate. If the beacon rotates one time every 40 seconds, what is the angular speed in radians per minute? Well, the first thing I want you to realize is that 40 seconds is equal to 2/3 of a minute. The other thing, because we're working in radians, I know that one rotation is equal to 2 pi radians. So in this case, when I want to know what that angular speed is, which is omega, we know that's equal to theta over time. And in this case, I know theta is going to be 2 pi radians over 2/3 of a minute. And so when I do that calculation, it's going to come out to be dividing by 2/3 is the same as multiplying by 3/2. So I have 2 pi over 1 times 3 over 2. And when I do that, it comes out to be 3 pi radians per minute. So that would be the angular speed for this lighthouse. One of the advantages to working with radians is it makes some formulas a lot easier to deal with. Okay, we've already talked about arc length. That arc length, when I work with this, I know that arc length S equals R times theta, where theta is in radians. What would happen if theta was in degrees? Well, in that case, what would happen is I would have to determine what portion of the circle I'm dealing with, and then calculate the circumference. So I'd have to take the angle measure, divide it by 360 to calculate the portion of the circle, and then multiply that result by the circumference. Where with the radian, if it's already in radians, all I have to do is take the radian measure of the angle, multiply it by the radius, and I would have my arc length, the length of that arc. The same thing is true about a sector. A sector is like a piece of pie, and it's a portion of the area of a circle. And so what we have with the area of the sector, when you're working in radians, the area of that sector is equal to 1/2 times r squared times theta. That right there is going to give you where theta is in radians. So in this case, when we're working with radians, it's a lot easier to calculate the area of that sector. Again, because if I was working with the degrees, I'd have to determine what fractional portion of the circle I had and then multiply it by the area. In this case, when I'm working in radians, this formula that I have here does all of that for me. It's already going through calculating all those pieces. So the radians make it easier to do calculations. And because we do that, because when we're working with radians, because of this, it does make other types of calculations, anything that needs the arc length of that area of that sector to do its job, it would make it a lot more efficient and a lot easier to work with. Finally, the last thing we need to look at today is a relationship between how our linear speed and the angular speed are related to each other. Well, to do that, we're going to start out with our definition that we have for a radian measure, that theta is equal to arc length divided by the radius. So solving for that, and then we get to our formula that we've talked about for arc length is S equals R times theta. If I then divide everything by t, I get S over t equals R times theta over t. Or I can write that as S over t equals R times theta over t. Now I want you to recall that S over t is equal to the velocity, and theta over t equals the angular speed, or omega. And so what this tells me is that my velocity, the linear speed, is equal to whatever the radius is times the angular speed. And the angular speed, omega, is equal to the velocity divided by the radius. In other words, both the velocity and the angular speed are related to each other by just, they are constant multiple of one another. So if I multiply the the angular speed by r, whatever r happens to be, that is going to be my velocity. Whereas if I multiply the velocity by 1 over r, that's going to give me omega. This now concludes the video that I have on our initial trig stuff with the angle measure. Please be sure to note the idea of what a radian is and the conversion factors. You're going to be dealing with that. We'll look at a couple more examples in class, but for the most part, in class, we should have a lot of time to work on just working with these different types of measures and answering some different types of questions. So I hope you are having a good day, and we will see you in the next class.